January 5th, 1943, 0900 hours, 47 miles southwest of Guadalcanal. Lieutenant Commander William Sterling Parsons stood on the bridge of the USS Helena, watching four specks resolve into ICD-3A dive bombers through his binoculars. The Japanese aircraft had just completed their attack run on the task force, one of them scoring a hit on the New Zealand light cruiser Achilles before breaking off. Now they were retreating toward Rabaul, climbing away at less than 200 miles per hour, already beyond what conventional anti-aircraft fire could reliably engage. What Japanese intelligence had reported to Tokyo about American anti-aircraft gunnery seemed to confirm everything Imperial Navy pilots believed. American gunners required thousands of rounds to bring down a single aircraft, their 5-inch shells detonated by mechanical time fuses set before firing, exploding at predetermined altitudes regardless of where the target actually flew. A pilot who changed course or altitude even slightly could watch American shells burst harmlessly in empty sky. The mathematics of survival favored the attacker. What those retreating pilots could not have known, what no Japanese commander had anticipated, was that the shells now being loaded into Helena's 5-inch guns contained something unprecedented in the history of warfare. Inside each projectile, protected by armor plating and shock-absorbing mounting, sat a miniature radar set smaller than a pint milk bottle. 5 tiny vacuum tubes, a transmitter, a receiver, and a battery that would not activate until the shell left the gun. The shell did not need to strike the aircraft. It did not need a human to guess the correct altitude. It only needed to pass within 70 feet of its target. Then it would detonate automatically, transforming a near miss into a kill. Lieutenant Cochrane, commanding Helena's aft 5-inch battery, tracked the departing bombers. He ordered 2 salvos fired at the retreating Japanese. The guns spoke. 3 shells arced across the Pacific sky toward an ICD-3A VAL that was already beyond what conventional gunnery could touch. The VAL's pilot never changed course. He had no reason to. He was well outside the range where American shells posed any danger. Then the sky around his aircraft erupted in synchronized explosions. At least one shell detonated within the lethal radius, sending a wall of shrapnel into the dive bomber's fuselage. The VAL shuddered, rolled, and began its final dive into the Pacific. No direct hit had been scored. The American gunners had missed, just as Japanese intelligence said they always did. But missing no longer mattered. Commander Parsons, watching from the bridge, understood immediately what had just occurred. The same officer who would later arm the atomic bomb aboard the Enola Gay had just witnessed the combat debut of what he considered an equally revolutionary weapon. In his report to Admiral William Halsey, Parsons wrote that the value of the Mark 32 fused projectile could not be too highly stressed. The era when aircraft could fly through anti-aircraft fire with relative impunity had ended over the waters off Guadalcanal. The transformation that began with that single VAL represented one of the most closely guarded secrets of World War II, a billion-dollar program that remained classified alongside the atomic bomb and D-Day invasion plans. By war's end, Japanese and German forces would suffer devastating losses to American artillery without ever understanding why their enemies' shells had become so impossibly accurate. They called it witchcraft, luck, superior optics. They never discovered the truth. The development of the VT proximity fuse, the variable time designation deliberately chosen to obscure its operating principle, had begun in August 1940 when Captain Gilbert Hoover of the Navy's Bureau of Ordnance approached the National Defense Research Committee with an urgent request. The Navy needed a shell that could destroy enemy aircraft without requiring a direct hit. The concept was simple. The execution was considered impossible. Rear Admiral William H.P. Blandy, Chief of the Bureau of Ordnance, captured the Navy's position in a memorandum that would become legendary among fuse developers. Here is something the Navy badly needs. Please go and get it for us. The field is wide open. We do not know how you are going to do it. If we did, we would have done it. The British had shared their research through the Teasard mission, transferring technology across the Atlantic in an act of wartime cooperation that would prove decisive. British scientists, including Samuel Curran, William Butemant, and Edward Shire, had conceived the idea of a radio-triggered fuse and built working prototypes for rockets. But their designs could withstand only 100 g of acceleration, while artillery shells experienced 20,000 g. The British had concluded that proximity fuses for guns were beyond current technology. The American team assigned to prove them wrong included some of the nation's finest scientific minds. Beyond WWII and Van Allen, the roster included Lloyd Berkner, who developed the separate transmitter and receiver circuits that made the fuse practical, and Richard Roberts, who conducted critical experiments on circuit reliability. Harry Diamond and Wilbur Hinman of the National Bureau of Standards developed Doppler effect techniques that became standard across all proximity fuse applications. Anti-aircraft gunnery in 1940 represented the military equivalent of throwing rocks at hummingbirds. The 5-inch .38 caliber gun, the Navy's primary anti-aircraft weapon, could fire 15 rounds per minute at targets up to 7 miles away. Each shell weighed 54 pounds and contained 7 pounds of high explosive. Yet against maneuvering aircraft at combat altitudes, conventional fuses proved nearly worthless. Time fuses required gunners to estimate target altitude, calculate shell trajectory, and set the fuse to detonate after a specific number of seconds. Any error in estimation, any course change by the target, any miscalculation by the gun crew meant the shell exploded in empty air. Statistical analysis showed that time-fused shells required an average of approximately 1,000 rounds to bring down a single aircraft. Against diving or climbing targets, the figure climbed even higher. Contact fuses, which detonated on impact, demanded the impossible, an actual collision between a 54-pound shell and a maneuvering aircraft traveling at 300 miles per hour. The Navy calculated that contact fuse ammunition was essentially worthless against aerial targets. What the Navy wanted was a fuse that could sense when it approached a target and detonate automatically at the optimal moment. Such a device would transform every near miss into a potential kill. The problem was that no such device existed, and physicists considered it technologically impossible. The fuse would need to contain a miniature radar set, complete with transmitter, receiver, amplifier, and power supply. This radar would need to fit inside a 5-inch projectile already packed with 7 pounds of explosive. The components would need to survive acceleration forces of 20,000 g when fired from a naval gun. They would need to withstand spin rates of 25,000 revolutions per minute as the shell's rifling sent it spiraling toward its target. They would need to function at temperatures ranging from -50 to +100 degrees Fahrenheit, and they would need to be manufactured by the millions at costs low enough for expendable ammunition. The British had attempted to develop a proximity fuse for anti-aircraft rockets, but their designs could only withstand 100 g of acceleration, far below what artillery shells experienced. Their research, shared with America through the Teasard mission, provided a starting point but no solution to the fundamental problem. Dr. Merle Tuve, a physicist at the Carnegie Institution's Department of Terrestrial Magnetism, received the assignment to achieve the impossible. His team, designated Section T of the National Defense Research Committee, began work in August 1940 with a small group of scientists and engineers who would grow into an organization of 800 personnel. The project would eventually involve more than 100 American companies, manufacture 22 million fuses, and cost over $1 billion in 1940s currency, roughly $15 billion in modern terms. The first challenge was miniaturization. In an era before transistors or integrated circuits, electronic devices relied on vacuum tubes, glass cylinders containing electrodes in a vacuum that could amplify electrical signals. The smallest commercially available tubes measured several inches in diameter. The fuse required 5 tubes that could fit inside a space smaller than a pint milk bottle while surviving forces that would shatter ordinary glass into powder. Physicist James Van Allen, who would later discover the radiation belts surrounding Earth that bear his name, spent nearly a year working on the vacuum tube problem. His team collaborated with Sylvania Electric Company to develop tubes less than an inch in diameter with walls of specially formulated glass thick enough to withstand the violence of being shot from a gun. Each tube was mounted in shock-absorbing material and potted in protective compounds. Testing involved firing tubes from cannons and analyzing which design survived. The results defied expectations. Tubes that shattered when dropped on concrete floors survived artillery firing. The key was the direction and duration of force. A tube falling on concrete experienced acceleration over milliseconds, allowing stress to propagate through the glass. A tube in a fired shell experienced the same forces over microseconds, too brief for the glass to respond catastrophically. The power supply presented equally daunting challenges. Dry cell batteries of the era lost charge over storage, meaning shells manufactured in 1943 might be useless by 1944. The solution came from National Carbon Company, predecessor of Union Carbide. Engineers designed a wet cell battery that remained inert until the shell was fired. The G-forces of launch shattered a glass ampule containing electrolyte fluid. The spinning of the shell then forced this fluid into stacked plates, creating a working battery precisely when power was needed. Safety systems required equal ingenuity. A fuse that activated prematurely could kill gun crews. A fuse that armed immediately upon firing could detonate dangerously close to friendly vessels. The solution exploited the shell's rotation. Critical components were deliberately misaligned until centrifugal force from spinning aligned them into working configuration. This meant the fuse could not arm until it had traveled far enough from the firing ship to be safe, yet armed reliably before reaching engagement range. The radio system itself represented a miniaturized marvel. The transmitter sent out a continuous radio frequency signal from an antenna built into the fuse's nose. When the projectile approached a target, this signal reflected back to the receiver. The intensity of the return signal increased as the shell drew closer to its target. When return signal strength exceeded a calibrated threshold, the fuse activated a thyratron tube, essentially an electronic switch, which released electrical energy stored in a capacitor. This energy triggered a detonator, which set off the main explosive charge. The entire sequence, from signal transmission to detonation, occurred in fractions of a second. The detection range averaged 60 to 70 feet for early models, increasing to 100 feet for later versions with improved sensitivity. This meant that a shell passing within roughly 70 feet of an aircraft would detonate, sending shrapnel in a lethal cone toward the target. By summer 1942, Section T had developed a working prototype designated the Mark 32 VT fuse. On August 12th, the newly commissioned light cruiser USS Cleveland began live fire testing in Chesapeake Bay. The targets were 3 radio-controlled drones maneuvering at combat speeds and altitudes. Standard anti-aircraft doctrine required hundreds of rounds to engage such targets with any hope of success. Cleveland's gunners brought down all 3 drones on the first day with only 4 bursts of proximity fused ammunition. The Navy canceled the remaining day of testing. There was nothing left to prove. Production began immediately at facilities operated by Crosley, RCA, Eastman Kodak, General Electric, and McQuay Norris. Early output reached only 500 fuse per day. By late 1943, production climbed to 40,000 daily. By war's end, American factories were completing 70,000 proximity fuses every 24 hours. Each fuse contained 130 miniaturized electronic components. The cost per unit fell from $732 in 1942 to $18 by 1945, a 97% reduction achieved through manufacturing refinement and economies of scale. The decrease reflected American industrial genius applied to mass production of devices that had seemed impossible 3 years earlier. The Navy imposed strict security on the new weapon. Fuses could only be used over water, where duds would sink beyond enemy recovery. The South Pacific received priority because Japanese forces lacked the technical sophistication to reverse engineer captured specimens and because the need was most desperate. American ships were dying under Japanese air attack, and the proximity fuse offered their best hope of survival. Commander Parsons personally escorted the first shipment of 5,000 fuses to New Caledonia in late 1942. He distributed them among the carriers Enterprise and Saratoga and the cruiser Helena, all vessels likely to face aerial attack. Personnel received training in handling and firing procedures. Then they waited for combat. The January 5th engagement off Guadalcanal validated every expectation. Helena's gunners destroyed a retreating dive bomber with their third salvo, a performance that would have required hundreds of rounds with conventional ammunition. Within days, reports flooded into Navy headquarters describing similar successes throughout Admiral Halsey's command. The gunnery report from Helena's engagement became required reading at the Bureau of Ordnance. The anti-aircraft control officer was convinced the shells had done their job. A Japanese VAL already beyond the range where conventional gunnery posed any threat had been destroyed by what appeared to be a near miss. The shell had detonated close enough to the aircraft that its blast radius, extending approximately 70 feet, caught the dive bomber in a spray of steel fragments traveling at lethal velocity. What made this engagement so significant was not merely the destruction of a single aircraft. It was the demonstration that American ships could now engage retreating attackers, could punish aircraft that had completed their attack runs and were fleeing towards safety. Previously, anti-aircraft fire was most effective during the approach phase, when aircraft flew predictable courses toward their targets. Once an attack was complete and aircraft began maneuvering to escape, the probability of successful engagement dropped precipitously. The proximity fuse inverted this calculus. Shells no longer needed to be aimed at where an aircraft would be at a specific future moment. They only needed to pass close enough. An aircraft that jinked left avoided the shell but not the blast radius. An aircraft that dove or climbed escaped the projectile but not the explosion. The mathematics of escape, which had always favored the pilot, now favored the gunner. Throughout early 1943, Halsey's ships accumulated combat experience with the new weapon. Night engagements against Japanese Betty torpedo bombers proved particularly illuminating. These twin-engine aircraft approached at low altitude to launch torpedoes, flying relatively straight courses that made them vulnerable during the final attack phase. But their speed and the darkness of the Pacific night had previously given them significant advantages. With radar-directed fire control and proximity-fused ammunition, American ships transformed night attacks into turkey shoots. Shells tracked by fire control radar exploded at precisely the right moment, regardless of whether gunners could see their targets. Bettys that had successfully launched torpedoes found themselves illuminated by the flash of proximity bursts, their crews killed by shrapnel before they could escape to safety. The statistics told a story of revolutionary change. During 1943, although only 25% of anti-aircraft ammunition issued to the fleet contained proximity fuses, these rounds accounted for 50% of Japanese aircraft shot down by shipboard guns. The fuses were 300% more effective than conventional time-fused or contact-fused shells. What Japanese pilots experienced was incomprehensible. Aircraft that flew through American anti-aircraft barrages suddenly began exploding without visible cause. Shells that clearly missed somehow destroyed their targets. Survivors reported the sky filling with perfectly timed bursts that seemed to anticipate every maneuver. Some attributed the phenomenon to American luck. Others spoke of supernatural intervention. None guessed the truth. If you are finding value in these lesser-known stories of American achievement, subscribing helps us uncover more. The transformation in Pacific anti-aircraft effectiveness accelerated through 1943 and 1944. During Admiral Halsey's night engagements against Japanese torpedo bomber formations, the VT fuse proved particularly devastating. Betty bombers approaching at low altitude to launch torpedoes flew directly into shells that detonated at precisely the right moment. Night attacks that had once enjoyed protection of darkness became suicide missions against radar, directed guns firing proximity, fused ammunition. Japanese pilot training programs, which had produced the finest naval aviators in the world before Midway, could not replace losses fast enough. The combination of combat attrition and training shortfalls meant that by mid-1944, replacement pilots arrived in combat units with less than 100 hours of flight experience. These inexperienced aviators faced American gunners whose weapons now killed without requiring direct hits. The desperation this created contributed to one of the war's most terrible tactics. In October 1944, Vice Admiral Takejiro Onishi authorized the first organized kamikaze attacks during the Battle of Leyte Gulf. The decision reflected cold calculation. Conventional attacks were failing because American anti-aircraft fire had become impossibly accurate. If pilots were going to die anyway, they might as well crash their aircraft into enemy ships. The kamikaze tactic temporarily restored a measure of Japanese effectiveness. A pilot committed to suicide did not need to escape after attacking. He could press his assault through the heaviest fire. Even if anti-aircraft rounds detonated near his aircraft, momentum might carry the wreckage into its target. The kamikaze threat reached its peak during the Okinawa campaign in the spring of 1945. Between late March and mid-August, Japanese forces launched 10 major kikusui attacks, meaning floating chrysanthemum, hurling thousands of aircraft at the American fleet in organized waves of suicide attacks. The intensity exceeded anything the Navy had previously experienced. American defenses adapted but could not eliminate the threat entirely. Combat air patrols intercepted many attackers before they reached the fleet. Radar picket destroyers stationed around the perimeter provided early warning and engaged with their own anti-aircraft batteries. The main fleet maintained multiple layers of overlapping fire, with 5-inch guns engaging at maximum range and smaller caliber weapons providing final defense. The VT fuse remained a critical component of this layered defense, but its effectiveness was constrained by the nature of kamikaze attacks. The shortened range and rapid closure speeds reduced the number of salvos that could be fired at each target. Fire control computers, designed to track conventional attacks, struggled with aircraft flying erratic approach paths at maximum speed. Despite these limitations, 5-inch guns firing proximity fused ammunition still accounted for approximately 15% of kamikazes destroyed. When combined with the 3-inch 50 caliber guns that also used VT fuses, naval anti-aircraft artillery destroyed a substantial portion of attacking suicide aircraft before they could reach their targets. American gunners adapted. The VT fuse remained effective against suicide attacks, but the shortened engagement time reduced the number of salvos that could be fired. 40mm Bofors and 20mm Oerlikon guns firing at shorter ranges became critical for final defense. Yet proximity fused 5-inch ammunition still accounted for approximately 15% of kamikazes destroyed by anti-aircraft fire, and 44% of all 5-inch kills used VT fuses. The mathematics remained overwhelming. Between October 1944 and August 1945, analysis indicated that 278 aircraft were destroyed by VT-fused projectiles. Conventional time-fused ammunition would have accounted for only 46 of these kills under identical conditions. The fuse multiplied effectiveness by a factor of approximately 6-to-1. The summer of 1944 brought the VT fuse to a new theater and a new type of target. 1 week after D-Day, German V-1 flying bombs began falling on London. These pulse jet-powered cruise missiles flew at 400 miles per hour at altitudes as low as 2,000 feet, presenting the most difficult targets anti-aircraft gunners had ever faced. British anti-aircraft batteries initially achieved kill rates below 20% against the V-1. Fighter aircraft proved more effective but could not maintain constant coverage. London was suffering dozens of hits daily, with each V-1 carrying 1,800 pounds of explosive. Section T modified fuses to fit British 3.7-inch and American 90mm anti-aircraft shells. Combined with SCR-584 automatic tracking radar and the M9 electronic fire control computer, the proximity fuse transformed V-1 interception. In the first week of VT-fused operations, anti-aircraft batteries destroyed 24% of incoming missiles. The second week saw 46%. The third week, 67%. By the final week of the V1 assault on London, anti-aircraft guns were destroying 79% of all incoming missiles. On the last day of large-scale V1 attacks against England, radar detected 104 missiles approaching the coast. 68 were destroyed by proximity-fused shells. Of the remainder, only 4 reached London. The VT fuse had saved the British capital from annihilation. General Frederick Pyle, commanding British Anti-Aircraft Command, later wrote that it was the proximity fuse which made possible the 100% success achieved on the best days of V1 interception. Without this American innovation, London would have continued suffering dozens of hits daily throughout the summer of 1944, with incalculable consequences for civilian morale and the war effort. When V1 attacks shifted to the critical supply port of Antwerp in September 1944, Prime Minister Winston Churchill authorized a special flight of Lancaster bombers to transport proximity fuses from Cincinnati to Europe. A single anti-aircraft battalion equipped with the new ammunition destroyed 48 of the first 75 V1s it engaged. The port remained operational without interruption for the remainder of the war. The release of proximity fuses for ground combat came during the German Ardennes offensive in December 1944. General Dwight Eisenhower had demanded permission to use the weapons against ground targets despite concerns about enemy recovery of dud rounds. The desperate situation of the Battle of the Bulge overrode all objections. 200,000 shells with VT fuses, codenamed Posit, entered combat within 2 days of the German attack. The effect was immediate and devastating. Artillery shells that previously exploded on impact with the ground now detonated 30 feet above German infantry formations. Shrapnel rained down on troops who had felt safe in foxholes and shallow trenches. Cover that protected against ground, burst artillery offered no defense against air bursts. American intelligence reported that German soldiers near Malmedy charged directly into artillery fire, yelling "Kamerad," preferring surrender to continued bombardment. Estimates placed German casualties from proximity fused rounds at 2,000 within the first week of employment. German commanders offered rewards for soldiers who could recover unexploded fuse, desperate to understand the American technology. Lieutenant General George Patton's Third Army employed the proximity fuse to devastating effect during the reduction of the Bulge's southern shoulder. On the night of December 25th and 26th, American artillery caught a German battalion attempting to cross the Sauer River near Echternach. Forward observers called for battalion concentrations using Posit ammunition. Patton later wrote to the War Department describing the results. "The new shell with the funny fuse is devastating. We caught a German battalion which was trying to get across the Sauer River with a battalion concentration and killed by actual count 702. I think that when all armies get this shell, we will have to devise some new method of warfare. I am glad that you all thought of it first." German prisoners of war consistently reported the demoralizing effect of the airbursts. One captured soldier described the attacks as quick, powerful bursts for which there was simply no defense. Another stated that troops refused to leave bunkers during artillery bombardment, paralyzing defensive movements. The 8th Infantry Division caught a German patrol in the Hürtgen Forest with a Posit time on target mission and found 96 German dead in the kill zone. The infantry soldiers who witnessed the new ammunition in action called it a Christmas present for the Germans. Observers watched shells explode 30 feet above German troops racing across a wooden bridge or paddling rubber boats across the Sauer River. Men who had felt safe in the open, protected from artillery by the cloud cover that prevented accurate observation, discovered that American shells no longer needed observers. They needed only to pass close enough to the ground to trigger their internal radars. The psychological impact exceeded even the physical casualties. German commanders reported that the effectiveness of the new VT fused shells exploding in midair on exposed personnel caused something approaching mutiny when soldiers started refusing orders to move out of their bunkers during artillery attacks. Troops who had experienced months of conventional artillery fire, learning to survive by seeking cover and waiting out barrages, found their accumulated experience suddenly worthless. Patton declared without reservation that the funny fuse won the Battle of the Bulge. From the lifting of restrictions until Allied forces crossed the Rhine, proximity-fused anti-aircraft fire brought down more than 1,000 German aircraft. In ground combat, the airburst capability transformed artillery from an area suppression weapon into an instrument of precision destruction. The proximity fuse program remained classified for months after the war's end. When the secret was finally revealed, military historians ranked it alongside radar and the atomic bomb as one of the three most important technological developments of World War II. Admiral Lewis Strauss wrote that one of the most original and effective military developments in World War II was the proximity fuse. The production achievement defied peacetime industrial expectations. By 1944, a substantial proportion of the American electronics industry concentrated on fuse manufacture. Procurement contracts grew from $60 million in 1942 to $200 million in 1943 to $300 million in 1944, and finally $450 million in 1945. More than 110 factories operated by 87 different firms participated in production. Each fuse required vacuum tubes manufactured to tolerances measured in thousandths of an inch, batteries that remained inert for months, then activated within milliseconds, circuits that survived 20,000 G acceleration followed by 25,000 RPM rotation, safety devices that prevented premature detonation during handling but armed reliably after firing. Quality control measured every component against specifications that would have seemed impossible before the war. The workforce that achieved this included thousands of women who had never worked in electronics before Pearl Harbor. Crosley Corporation employed over 10,000 workers at peak production, many of them women operating precision assembly equipment. Their output reached 16,000 fuses daily from a single company. The democratization of American industry, integrating workers regardless of gender or background into high-precision manufacturing, proved as revolutionary as the technology itself. Japanese military intelligence never understood why American anti-aircraft fire became so deadly. German engineers captured doomed fuses but could not replicate the technology. More than 30 different proximity fuse designs were researched in Germany during the war, including acoustic fuses triggered by engine sound and electrostatic fuses based on capacitance effects. None reached service. The Germans concluded that artillery-launched proximity fuses were technically impossible because vacuum tubes could not survive the acceleration forces. They were wrong, but their error was understandable. American scientists had achieved the impossible. At the Smithsonian National Air and Space Museum today, a Mark 58 proximity fuse, donated by Dr. James Van Allen, displays its miniaturized electronics in a cutaway exhibit. The placard explains how this device, smaller than a pint milk bottle, contained a complete radar set capable of surviving forces that would crush ordinary electronics. Visitors can see the tiny vacuum tubes that Van Allen helped develop, the shock-absorbing mounts that protected fragile components, the ingenious battery that activated only when the shell was fired. What the display cannot convey is the impact this technology had on men who faced American fire without understanding its source. Japanese pilots who watched their wingmen explode without visible cause. German soldiers who saw comrades killed by shells that missed them by dozens of feet. Commanders who ordered attacks into anti-aircraft fire that never seemed to miss. January 5th, 1943, 0900 hours, 47 miles southwest of Guadalcanal. A Japanese VAL pilot retreated from his attack run, confident he had escaped American gunnery. He was beyond effective range. American shells always missed at this distance. Every pilot knew that. Helena's guns fired 3 rounds. The shells did not need to hit. They only needed to pass within 70 feet. The pilot of that VAL became the first victim of a weapon that would help destroy thousands of Japanese and German aircraft, save the ports of London and Antwerp from V1 annihilation, devastate German infantry formations in the Bulge, and contribute to forcing Japan toward the desperate strategy of kamikaze attacks. He died without understanding what had killed him, struck down by a technology that enemies considered impossible. By war's end, the proximity fuse had transformed from theoretical concept to mass-produced weapon manufactured at 70,000 units daily. American factories had achieved production levels that German and Japanese industries could not have matched even if they had solved the engineering challenges. The combination of scientific breakthrough and industrial capacity that defined American strength in World War II found perfect expression in the VT Fuse program. The Japanese pilots who attacked the fleet off Guadalcanal in January 1943 had believed American anti-aircraft fire posed minimal danger beyond close range. By August 1945, there were few Japanese pilots left to test that belief. The proximity fuse had helped kill them, one near miss at a time, turning the sky itself into an American weapon that never revealed its secret until the war was won. Admiral Arleigh Burke, who would later become Chief of Naval Operations, served as Chief of Staff to Vice Admiral Mark Mitcher, commanding the fast carrier task forces during the final year of the Pacific War. In a 1978 interview at the Applied Physics Laboratory, Burke reflected on the fuse's impact. When I went as Chief of Staff to Admiral Mitcher, all the 5-inch 38 and 5-inch 25 ammunition was fitted with VT fuses, and as you well know, those fuses knocked down enemy planes by the dozens. The Japanese military never developed an effective countermeasure or even a complete understanding of what they faced. Post-war interrogations revealed confusion among surviving pilots about why American anti-aircraft fire had become so devastating. Some attributed it to improved radar. Others believed Americans had developed optical tracking systems of unprecedented accuracy. None guessed that the shells themselves contained the secret. German engineers who recovered DWII fuses from battlefields in Europe attempted analysis, but concluded the devices could not possibly work as suspected. The acceleration forces of artillery firing would destroy any vacuum tubes, they reasoned. Their scientists had tried and failed to develop gun-launched proximity fuses. Therefore, the American devices must operate on some other principle. This failure of enemy intelligence proved as decisive as the weapon itself. Without understanding the fuse's operating principle, German and Japanese forces could not develop countermeasures, could not employ jamming, could not adapt tactics beyond desperation, measures like kamikaze attacks. The legacy of the proximity fuse extended beyond World War II. The miniaturization techniques developed for VT fuses became foundations for post-war electronics. The vacuum tubes that James Van Allen created to survive artillery firing led to his interest in radiation-resistant components, which ultimately took him to the discovery of Earth's radiation belts. The Applied Physics Laboratory that WWII established became one of America's premier research institutions, continuing to develop advanced weapons technology through the Cold War and beyond. Commander William Parsons, who had witnessed the first combat use of the fuse off Guadalcanal, went on to arm the atomic bomb that destroyed Hiroshima. The connection was not coincidental. Parsons brought the same meticulous attention to detail, the same insistence on practical testing, the same bridge between laboratory science and combat application that had made the proximity fuse possible. The statistics compiled after the war confirmed what combat experience had demonstrated. 5-inch guns firing proximity fused ammunition required approximately 500 rounds per aircraft destroyed against conventional attacks, and somewhat fewer against kamikazes flying predictable approach courses. Non-VT fused 5-inch ammunition required approximately 2,000 rounds per kill. The 4-to-1 advantage in efficiency translated directly into ships saved and sailors' lives preserved. 22 million fuse were manufactured during the war. Each contained 130 individual components assembled to tolerances that challenged American industry to achieve. Each was tested, shipped, and employed in combat conditions ranging from the tropical Pacific to the frozen Ardennes. Each represented a combination of theoretical physics, practical engineering, and mass production capability that no other nation could have matched. January 5th, 1943. The date when American anti-aircraft gunnery transformed from desperate barrage fire to precision lethality. The date when enemy pilots learned, though they never understood why, that the sky had become hostile in new and terrible ways. The date when a Val dive bomber died 47 miles southwest of Guadalcanal, struck down by a shell that missed but killed anyway. The Japanese called American marksmanship lucky. The Germans called it impossible. The Americans called it Section T, and they kept it secret until the war was won. By then, there was nothing left to hide. The proximity fuse had proved what American science and industry could achieve when national survival demanded the impossible. It had transformed near misses into kills, turned anti-aircraft gunnery from statistical improbability into reliable lethality, and helped destroy the air power of two enemy nations while they struggled to understand a weapon they never saw coming.